Okay, so does this microphone work? Yes. So thank you everyone for being here for the last Science Cafe of 2017. And it's very nice to have here Professor Rami Vainio from the University of Turku. He will talk about Finnish nanosatellites.
Okay, so good evening everyone. I will talk a little bit about Finnish nanosatellites now for half an hour as a new possibility for sustainable use of space. And I hope that this will become more clear what is the possibility of unsustainable use of space with these nanosatellites. So this is a cover of Science magazine from 2015 noting that CubeSats take flight. This is something that has made the use of space much more democratic than it used to be, because access to space has suddenly become very, very cheap compared to the old times when launchings of spacecraft always cost something like tens of millions or so. And now you can get into space with small satellites or nanosatellites, as we call them, with less than 100,000 euros. And this has really made it possible for all kinds of activities which are new, utilizing space. And first, a little bit about CubeSats. What are CubeSats? They are small satellites which are made of units of 10 times 10 times 10 centimeters. So 1 liter units of hardware. They can be combined into different types of systems, and they fall into sort of general classification of spacecraft or satellites, which is given there. So that a mini satellite is normally a satellite which weighs 100 to 500 kilograms, and larger than 500 would then be a large satellite. Microsatellite is about 10 to 100 kilograms. Nanosatellite is 1 to 10 kilograms. Picosatellite is 0.1 to 1 kilograms, and then even femtosatellites have been discussed. All CubeSats fall into the middle categories. So picosatellites, if they are 1 unit systems, nanosatellites if they are 2 unit or 3 unit systems, and finally microsatellites if they are 6, 12 or 27 units systems. So the classification is there by the maximum weight that the launch providers usually allow for these type of satellites. And as the number in front says, it tells you how many 10 by 10 by 10 units you have in the system. Now in Finland, the development of nanosatellites has been started in Aalto University, and there are 2 spacecraft which have been launched to space, Aalto 1 and Aalto 2, and they are nanosatellites, so they are 3 unit Aalto 1 and 2 unit Aalto 2 CubeSats. And these are the first Finnish satellite projects that made it to space. So there have been some earlier attempts in the 80s and 90s to design satellites, but because at those times satellites were so expensive to build and to launch in space, all these projects have been buried before launch. But now, with much more affordable access to space, it has become possible to take these projects until the end and launch them into space. Now Aalto 1 was started already in 2010, actually, this project. And Aalto 2 was started a couple of years later, but due to some unforeseen conditions with the launch provider, actually what happened was that Aalto 2 was the first to make it to space. So Aalto 2 made it first. It is a 2 unit CubeSat, and it's built in Aalto University in Espoo, but the payload, the scientific payload of this is a plasma instrument called multi-needle Langmuir probe, and it's provided by the University of Oslo. This is a part of so-called QB50 project, which is a EU-funded project for launching a large number of nanosatellites to investigate the Earth's atmosphere. And this large number was supposed to be 50 in the beginning, but in the end there were 27 satellites launched. So not all of the projects were actually successful in the end. And the Aalto 2 satellite is registered in Belgium for this reason. So it's actually not a Finnish piece of hardware in orbit. And so that was built in Finland, but registered for Belgium. And it was because it was an EU project and led by a Belgian institute. It was launched to space in 18th of April this year, and it arrived at the International Space Station 5 days later, and it was released on its orbit from the station on 25th of May. Unfortunately, the contact to the spacecraft was lost only 1 week after that. So 1 week of operations, checking that the systems are working well, were basically the only things that we could do with that satellite, and after that it was lost. Probably due to some malfunctioning of the communication system. So then, Aalto 1. Aalto 1 is the first, or the first starting project. It's a 3-unit CubeSat, and it weighs about almost exactly 4 kilograms, which is the maximum allowed mass for this type of 3-unit CubeSat. The dimensions are, the height is 34 centimeters. For some odd reasons, 3-unit CubeSats are allowed 4 extra centimeters, not 30. And then 10 by 10 is the footprint. And it carries 3 payloads. One of them is a spectral imager called AASI, provided by VTT. Another one is Radmann radiation monitor, which is built in the University of Turku and partly in the University of Helsinki. And then finally a plasma brake, which is a novel deorbiting device, which I will talk a little bit about later, which is an innovation by the Finnish Meteorological Institute and is the 3rd payload of the system. In addition, it has all kinds of subsystems, as you can see in the picture. So there are 2 radios, UHF radio, an S-band radio, and then 2 antenna systems related to that as well. There is a redundant or doubled Linux computer on board, and attitude control system, electric power system, in addition to the scientific payloads. These electron guns that you see here are part of the plasma brake experiment. I will explain that a little bit later. So, we started the project already in 2010 in January. And it was basically an educational project. So all of the people who were actually working on the satellite itself were students from Aalto University, from BSc level to finally to PhD level as well. But everybody started at BSc or MSc level. So the first years were really steep learning for the crew. And then from the payloads VTT project for the spectral camera, that was sort of a professional, or not in quotes, it was entirely professional kind of space hardware project, so no students involved. But then as well as plasma brake, that was also something that was done by people who have already experience in space hardware. But Radmann was also, radiation monitor was also a student project built in the University of Helsinki and Turku. And all this resulted in a little bit delayed schedule, probably because a lot of things had to be learned during on the way. So the first plan was to make it ready in 2 years, then launch. Finally, it was delivered to the launch broker, the flight model, in May 2016. So 6 years later than the start of the project. And then the original launcher was Falcon 9 from SpaceX company, and that launcher had that rocket had a lot of problems at the time when Aalto 1 was supposed to be launched. And in spring or let's say winter this year, early January or February or so, we made a decision to shift the launch from SpaceX to an Indian launch provider. And that was really smooth and rapid. So after the decision was made, it took only less than half a year and the spacecraft was in space. So the satellite was launched on Midsummer Eve 2017. And the launcher is this Indian PSLV rocket, and this one was the 38th rocket of that type that was launched from India. It delivers the payload to a polar orbit, meaning that it crosses the poles of the, it's on a semi or almost circular orbit, quasi-circular orbit around the sun, around the Earth, and at an altitude of about 500 kilometers, and going above the poles of the planet all the time. And it was deployed at 7:22 from Finnish summertime, actually, from the rocket to the orbit. And this orbit is sun synchronous. And what does it mean? It means that the orientation of the orbit when the Earth revolves around the sun stays constant with respect to the sun. So it means that the orbital parameters are such that the slight non-spherical shape of the Earth is not entirely spherical, it's a little bit oblate. And this oblateness is enough to produce a gravitational term or gravitational force term, which can actually yield a torque to the orbit, so that the orbit progresses around the sun at the same pace as the Earth revolves around the sun. So that this green orbit that you can see around the Earth is maintaining its orientation all the time with respect to the sun, which is very nice, because if you are making observations of the Earth, you have constant illumination conditions on your track. So the planet has the same type of illumination all the time below the spacecraft. And that's one of the payloads is a spectral camera, which is taking pictures of the Earth. This is a very good advantage of the orbit. The mission was, the first contact to the mission was established only hours after launch or deployment from the rocket. And this is a picture of the control room when the first contact was established during the first overpass of Otaniemi. So basically the ground station is in Otaniemi, in Espoo, and you can only have contact with the spacecraft when it's flying above Otaniemi, and it's not actually occurring every orbit. This type of polar orbit usually has 90-minute period, so it takes 90 minutes for the spacecraft to revolve around the Earth. But because Earth is rotating faster than than the orientation of the orbit, it means that the Earth is rotating below the spacecraft, so that you are not every time getting the spacecraft above you. And this means that you can have good contacts with the satellite only twice a day. And about, let's say, 20 minutes in total per day. And the current mission status is the following. So the satellite is still in a tumbling state. This means that there is no active attitude control at the moment. There are some firmware updates that we have to upload in order to get a better attitude control operating, and that has not been done yet. So all critical systems for satellite are working properly, and most subsystems are commissioned, meaning that they have been tested and used for some time. Only the low gain antenna and the UHF's radio system are now in use. This is because of the attitude control, missing attitude control. So the S-band radio, which would have much more bandwidth, has a directing antenna. So it's basically so that you have to maintain control in order to be transmitting with that antenna. If your spacecraft is tumbling, you cannot use that system yet. The highest priority is set to main payload demonstration. So we have demonstrated both the radiation monitor and the spectral camera, and then all in all, the conditions in space in Aalto 1 are very stable and very nice. Batteries are fully charged most of the time, and temperatures are very stable. So everything looks more or less okay. So this is the first payload now. It's the spectral imager Aasi. It has basically two cameras. One visual camera, which is like a webcam, not that bad, but basically just a normal color camera. And then a spectral camera, which is able to take waves at certain wavelengths. So the bandwidth is only 20 nanometers, and the wavelength range is the visible range from 500 to 900 nanometers. It weighs about 600 grams, so it's very miniaturized device. Usually these type of spectral cameras weigh many kilograms, and the power consumption is 2.5 watts, which is also basically 1/10 of what you are used to in these type of applications. So it's a very advanced kind of thing. Now, because of the tumbling state of the spacecraft, it's not possible to take controlled pictures with this camera because it's pointing everywhere. Basically, the rotation of the spacecraft is such. But we just shoot around, and the first picture was taken and downloaded in July. And this is taken with the visual camera of the device, and it's a coastline somewhere in northern Norway. Somebody might be recognizing that. I cannot actually recognize it, but nevertheless, it's been recognized where the picture is from. So it's 516 kilometers over the northern Norway with the visual camera. And you can see you can make some features of the coastal line there, so you can get an idea what is the resolution of that camera. But of course, because it's tumbling, it's rotating fast, it is not possible to take so nice pictures. But nevertheless, the spectral images have also been obtained, so we have been taking pictures. Now these are the first spectral images downloaded. One of the problems with this is this tumbling state, not only the pointing, the other one is that because we cannot use S-band radio, which would have a very good bandwidth, a lot of data coming down, telemetry rate would be high, we are using the UHF radio, which has a telemetry rate of 10 kilobaud. So you can understand that this is a very slow process of transmitting these pictures down to the Earth. So it takes a long while, large amount of passes. Fortunately, of course, these pictures don't have to be downloaded all at once. You can download them in pieces, and that's what we have done. So here the black and white pictures are taken at a single wavelength, and the joint picture is such where you have used a different color for one image and a different for the other and combined them. And you can see some shades, some little bit of color changes in the picture, which indicate that some at a certain wavelength there is more emission than at the other. So the color change shows that it's not like uniformly the same spectrum from all the points. And this is actually the way these type of spectral cameras are used in order to study the Earth. So Earth, different types of things in the ground are emitting in different wavelengths, and it's possible to do all kinds of practical application using spectral cameras. You can use them for agriculture, you can use them for all kinds of things like snow, things like that, in order to study how are the conditions below the spacecraft. So that is the idea of the use for this type of devices. There is this plasma break, which is the second payload, or one of the payloads built by the Finnish Meteorological Institute. Its mass is about 260 grams. It's a small device. It's basically a reel of 100 meter of hair-thin tether, and a little point mass in the beginning of the tether. And in the end of the mission, it will be unreeled. So we have 100 meters of tether coming out from the spacecraft. So what's the idea of that? The idea is that you charge using the electron guns, which are able to eject electrons from the spacecraft, negatively charged particles away from the spacecraft, which means that the spacecraft itself, as well as the tether, become, well, probably just the tether, become positively charged. So you have a positively charged tether, and the satellite is going through the ionosphere, the highest part of the Earth's atmosphere, where the gas is consisting of charged particles. So you have ions there, which are also positively charged. So there is a repelling force between the tether and the ions. And this actually makes the effective length of this tether, I mean the length or the width at which it can still interact with the ions is much, much larger. It's tens of meters instead of being just this a few micrometers or a few tens of micrometers as the tether thickness. So in effect you have a big thing, electrostatic thing in your spacecraft which is interacting with the medium and providing a drag. So you get a drag which is slowing down the spacecraft, and you are slowing down the spacecraft means that it's going to a lower and lower orbit until it finally hits dense parts of the Earth's atmosphere and burns down. So this is a method or a device which is used to bring down the spacecraft from the orbit. If you would leave it there, just without this tether, you would actually, in 500 kilometers, it would stay there for years. And this would mean that it's actually orbital debris after it stops working. Okay, the third experiment we have on board is Radmann, which is the one that has been built by my research group. And this is done in the University of Turku and the University of Helsinki. And it's a particle detector measuring the flux of 700 keV electrons and 10 MeV protons. What does it mean? Electrons and protons, the constituents of the hydrogen atom, these energies for these particles mean that they are propagating at, electrons especially are propagating at almost the speed of light. For protons, they have a velocity which is about 15% of the speed of light or more. So these are very, very fast particles, and they are particles which can penetrate a lot of material. That makes them dangerous. That makes them particles which cause ionization in all spacecraft electronics and things like that. And it is this type of space radiation that is mainly responsible for satellite malfunctions. So this is the motivation to study these in orbit. It's also a very small one, so 350 grams power consumption, 1 watt, which is also something that is much less than for typical devices of this type. Okay, so here's the picture of the Aalto 1. Take now away all the spacecraft hull. You are left with the subsystems here, so you can see that it's a tight stack of stuff. And there on the left you have 2 payloads. On the upper part you have the plasma brake, this part, and then this lower part here is Radmann. And Radmann looks like that. It's a radiation monitor which is basically analyzing all the particles that hit this part of the detector, which is the active detector element. And the rest is electronics to analyze the signals. And the operation is very simple. You have 2 types of detectors which are able to measure the energy that was deposited in this material. One is the silicon detector, which is a very thin one here, and the other one is very bulky. Well, this is a 1 cubic centimeter. It's a bit bigger there. A cubic centimeter detector called a scintillator. It means that it's the particle deposits its energy in this detector here, and that is converted into a light pulse. That light is propagating in the detector and hitting this light diode here, so photodiode, and that turns that light pulse into an electric pulse. And these 2 electric pulses, the one that you get from the silicon detector and the one that you get from the photodiode, can be analyzed together. Their sum represents the total energy of the particle, and if you compare the pulses with each other, you can actually deduce what is the type, electron or ion or electron of the incoming particle. So you are able to make a measurement of all the particle fluxes that hit the detector. Now, first, let's say, radiation storm that we got with Aalto 1 was, we were pretty lucky. After about 2 months in orbit or a little bit more, Aalto 1 faced one of the biggest radiation storms of the whole sunspot cycle. So the sun has activity which has an about 11-year cycle, and this is a very, very quiet phase of the solar activity. So we were pretty lucky to get one pretty big storm coming out from the sun and actually disturbing the environment in the near Earth space. Now, what you can see there is a measurement of energetic particles. So these are protons measured at energies more than 100 MeV, 50 MeV, and 10 MeV. 10 MeV proton flux is the threshold which we are measuring with Radmann. So the uppermost curve represents things that would be measurable by Radmann. But these are not measurements by Radmann. They are measurements at the geostationary orbit, which is 6 Earth radii, so much, much more than 500 kilometers away from the surface of the Earth. So at 36,000 kilometer altitude. And now we are making measurements with Radmann and with Goes, which is the geostationary satellite, and comparing this one and that one allows us to see how well our measurements, the red dots, are tracking the measurements of the geostationary orbit. And you can see that, okay, it seems to follow, the flux curve seems to follow, but there are these pauses. So there are periods in between which do not show any fluxes, and the explanation is here. So our low Earth orbiting satellite is actually protected by the magnetic field of the Earth. So what happens is that most of the orbit, we are here, where you see these dark or dark blue colors, it means that there are no counts in the detector. And it is because the Earth's magnetic field is providing protection, and the particles coming from the sun cannot enter the orbit. Only through the polar regions here we can get to measure the proton storm. And that explains why we have these pauses here. So for example, now if you would take one more time. So the proton storm can be only observed here on the upper parts of the orbit, and the spacecraft is actually flying so that it's going this way. So the arrows there point how the spacecraft is flying through the proton storm. Now the first 6 hours here have been simply mirrored there. So the same picture cut off and put here, and you can see the same fluxes here. And now I have indicated with arrows the times during which these polar passes are measured. And we can see that we measure about the same flux as is measured by Goya at the geostationary orbit. A little bit more, which is understandable because there is some magnetic protection also at geostationary orbit. And this is why we are not measuring exactly the same flux, but a little bit more when we are at the poles of the sun, of the Earth. Now here's a dot which is always there. That's the so-called South Atlantic anomaly. Above Southern Atlantic and Brazil, you have a region where there's always radiation, always. This is the trapped radiation of the Earth's magnetic field. So it not only provides protection from radiation coming from the outside, but it also traps radiation that somehow manages to get in. And the protons that are in these radiation belts have been born in a peculiar way. So a very high energy cosmic ray particle has hit the atmosphere of the Earth, produced an albedo neutron. The neutron is non-charged particle. It can travel out, but it decays. It decays into a proton and an electron, and these are immediately trapped by the Earth's magnetic field. So you get a trapped radiation belt around the Earth.
Can I ask why there? Why there?
Yes, I can explain. So no, it would of course, if the Earth's magnetic field would be a totally symmetric dipole, it would be a situation where you would see everywhere or probably nowhere because you lose the particles that touch the atmosphere. But the problem is that there is one place there where the magnetic field is weaker. And this means that the particles can get closer to the Earth's atmosphere at that altitude. And that's where, because at the same time when they are sort of trapped into the magnetic field and perform so-called bounced motion, they are also orbiting around the Earth. So they are drifting around the Earth, these charged particles, at the same time. And every time they come above this region, they have a possibility to come a little bit closer to the Earth because of the weaker magnetic field there. Okay, this was not the only observation which we have made. We also made observations during this storm a little bit earlier. Now this is a period of time when you can see the Goya's fluxes of electrons and magnetic field measurements here. And in the upper panel, you see the protons. So now, if you look at this thin stripe here, that's blown up there in the in Radmann observations here in the upper corner. So this one gives what Radmann sees at the time when the Goya spacecraft see that type of fluxes and magnetic field. So this is basically one of those, or two of those peaks that we observe. And now Aalto 1 has an orbit which is very close to the Earth's surface at 500 kilometers. Goya is measuring here, and this is a picture now of the magnetic field lines around the Earth. This is Earth's magnetic field. It's basically this type of a dipole field, which you would get also from a bar magnet. So you can imagine there is a bar magnet inside the Earth. And this bar magnet is not in the center, it's a bit off the center, and that's why the one region here has a weaker magnetic field, and there is a maximum of the magnetic field on the opposite side of the globe. So this part here is observed when Aalto 1 was passing the North Pole. Now, this part in the middle is when Aalto is passing these central latitudes here, and then the final part, when the fluxes are high again, is when Aalto is passing the South Pole. And this is how it goes. So this is how we explain how the fluxes go up and down. Now, during the same storm, about a week later, we had a situation when the proton fluxes at the geostationary orbit suddenly decreased. At the same time, there was a huge disturbance in the magnetic field measured by the Goyas. And this actually indicates that there was something, a very big disturbance of the solar wind hitting the Earth's magnetosphere. So the magnetosphere reacted immediately. The magnetic field of the Earth compressed on the day side, and that was actually visible in this peak here. So what does that yield in Radmann measurements? So we were seeing this type of measurements with our instruments, and now we had broken these into different types of particle channels. The ones with dashed curves are electrons, the ones with full curves are protons. And you can see that we have, in addition to these polar passes, like this one here, where the fluxes are mainly protons, and the one that you have here is also a polar pass, and the fluxes are mainly protons, so the highest curve is a full curve there, below the black one, which is a total. Then we have these ones, which are electrons. So somehow now, in these middle latitudes, we suddenly have electrons coming in our instrument. And the fluxes are very high. This is a 10-fold increase over the proton flux. What do we have there? We have the radiation belts of the Earth. This is the inner belt of the Earth is here. This is the part where you get the South Atlantic anomaly, so they touch the Earth's surface around here. And now there is another belt, a so-called outer radiation belt, which is filled with MEV electrons, and these are now, for some reason, precipitating, getting to our low altitudes where Aalto can see them. And why is that? It is because of this magnetic disturbance. So the magnetic field gets disturbed, and the electrons are sort of raining down from their sort of stable orbits to the atmosphere. And you can also see it nicely the same night. This is an all-sky camera from Hankasalmi taking photographs of the full sky. And around here you start to see the green light, and that's Aurora. So the same particles that we measure with Radmann 500 kilometers above the ground are seen as Aurora in the atmosphere from below, because these electrons are hitting the atoms of the atmosphere and producing excited states, and these excited atoms will release light at certain wavelengths. So what? Electrons and protons are raining down to the atmosphere. What is it just nice curiosity and Aurora? No. Actually, they produce ionization in the atmosphere. And this means that you will also get some atmospheric processes because of that. So protons and electrons from the sun or the magnetosphere will rain down. We have some nitrogen oxides, hydrogen oxides produced by these ionizing particles, and they are actually cut out. They are particles which can catalyze reactions destroying ozone. The total reaction that happens is that you take 2 ozone molecules and you convert them into 3 regular oxygen molecules. And this is actually something that is very important for the radiative balance of the atmosphere. And you can actually observe these things affecting regional climate. Not the global one. We are not talking about global warming here, which is man-made, but regional changes in the climate is possible to correlate with these precipitations of the particles. And this is an established fact. Aalto satellites also have commercial spin-offs. So there are radar satellites produced by the company named IceEye. These are a little bit bigger, about 100 kilogram satellites, but nevertheless they have a very good radar technology which allows them to make Earth observation, and they have been able to get about 13 million investments, which they announced in August. The guys there come from Aalto 1 project. Another spin-off is Reactor Space Lab, which is also people coming from Aalto project, and they are designing a nanosatellite-based hyperspectral imager constellation, and also getting a lot of interest from investors. And I can say that space is an emerging megatrend growing as fast as clean tech. Now the future, in summer we got knowledge that we will get actually funded for a Center of Excellence in Research of Sustainable Space. This is going to be an 8-year effort led by Minna Palmroth from the University of Helsinki and participated by University of Turku, Aalto University and Finnish Meteorological Institute. And basically we are tackling this thing here. Here you can see the launches from the 50s up to 2014. And you can see that here, the number of launches picks up suddenly. It's about 300 per that year, 2014. Now the number this year is 600. Most of them are commercial launches and most of them are nanosatellites. This is actually a sustainability problem. And this commercial new space has to deal with this really quickly. Now this looks like a bullseye in the windshield, but it's actually a picture of the International Space Station's window being hit by a debris particle in orbit. A tiny particle hitting the window will make this type of mark. This is the distribution of all known debris particles around the Earth. So you can see, although of course the particle size has been overestimated, but you can see that the number of particles, known objects, is huge. And now we are talking about particles which are greater than 10 centimeters across. If we are talking about particles of millimeter size or something like that, this is growing to much higher sizes. So debris in orbit is really a problem soon, because we cannot find safe place in the orbit anymore. Another thing which is very important is that radiation, as I already mentioned, is very dangerous to spacecraft. All these new space satellites, these nanosatellites, are built from commercial components, which means that they are very vulnerable to radiation. And they have problems when facing high fluxes of radiation. We have witnessed that with Aalto. Every time we get very high fluxes, the rate of computer boots gets high because of single bits in the memory flipping and the spacecraft realizing that it has to boot itself. So this is actually something that occurs all the time. And of course, these type of things are dangerous because at some point you may actually lose the spacecraft and it becomes debris in orbit. And this is the combined picture, so the radiation belts and the debris. These are the things that we are going to tackle in the future years with the Center of Excellence. And we will combine the physics of the radiation, its genesis, its transport, its precipitation into the atmosphere. So this type of physics with the technology development to cope with the radiation and to really build this device that is able to bring down the spacecraft from low Earth orbit into the atmosphere where they burn, and we can get rid of them and not produce more debris in space. Yeah, thanks.
Thank you very much for the very interesting talk. And now, as usual, we have questions from the audience. I have some questions, but I will shut up and wait for you first. Yes. Can you use this just for the recording?
Yeah, sure. Basically, you explained the Aalto satellite, but I couldn't understand how it is powered. Do you have the solar panel surrounding it?
Yes, yes, good question. So we can go back. I didn't show that, but the picture of the satellite shows it actually. Let's go back to, actually it's better seen in this one. So the spacecraft, these black ones here are also solar panels. So the long sides of the spacecraft are covered with panels, solar panels. There are some places where we have instrumentation and S-band antenna and things like that, which are not covered by panels, obviously, but it is enough, this amount of coverage with panels is enough to provide about 8 watts continuously. So the peak is more, but because we are on the night side every now and then, we can sort of take power from the batteries at 8 watt all the time.
So more questions? Yes. Wait a second. I'm arriving. Yes, he's arriving.
About tumbling, was that expected that it would be tumbling this much, and will it be controlled?
Yes, it was expected. What was not expected is that the attitude control system boots every 60 seconds. So we need a firmware update in order to be able to actually get it under control. And
there's two-way information you can upload and download?
We can upload, but using the UHF, 10 kilobaud. And things have to be done very carefully because we don't want to, because of this update, we don't want to lose the whole spacecraft. All these kind of things where you are messing with things inside the spacecraft have to be done very carefully. There are a number of examples where people have messed these things up and lost the spacecraft. And because this is actually still a student project, it's operated by Aalto University students, it is also something that needs to be taken into account. So not professional people are operating the spacecraft, which means that Professor Jan Brax is very careful of letting them do things with the configuration now that it's basically working. So the attitude control system uses so-called magnetic torgers, which means that they have small current loops which can, when reacting with Earth's magnetic field, can produce a torque. And these torques are not very large. So if you can apply the torque only for 60 seconds, you can't really slow down the tumbling at the time, because then it boots and then you have to do it all over again with another telecommand up. So it's very slow process until we get the firmware update. The good news about this is that there is another satellite using the same attitude control system, and they were launched later, so they were able to get the firmware update before launch, and it works. So we know that once the firmware update is up there, we can actually manage to get it under control. But so far, This is actually very good for Radmann because we don't care where we look. Radmann experiment enjoys this omnidirectional view of space, and our telemetry rate is also pretty low because it's just fluxes, it's not pictures, so we can survive with 10 kilobaud greatly. So I suspect that once the tumbling is taken care of and we return into this mode where we are 3x stabilized or established, that then the mission will concentrate on ASI, on the spectral imager, and not so much on Radmann anymore.
Actually, I have a question related to what you were saying. I like very much that this is a student project, but I was wondering, do you have some specific programs to, like, say, teach the students, and is it something that is run by Aalto? How is the Turku-Aalto interaction going, and are they just learning by doing?
Yeah, so Aalto has space technology as one of the major, or you can major in space technology. Turku has nothing like that. So in Turku it's all ad hoc. But because we are in collaboration with them, and because there are many people in our group who have lots of experience with space hardware from previous projects, we have been building instruments for big satellites for a long time. So here they are basically learning by doing. So there is no formal education because space technology cannot be one of the topics that you can award a degree. So that's it.
Yes. So more questions?
What's the expected lifetime of Aalto 1?
Hard to say. So far, we have not seen any subsystems permanently fail. So we have these what we call single event effects. So some bit flips in the computer, but they are simply upsets of the bits, meaning that bit can be turned, but once you reboot the system, it will be initialized with the correct image again. So there is no permanent damage from the radiation, but who knows? It could be that the components fail.
But was the spacecraft designed to last for a particular period of time, or was it?
It's commercial components. There is no guarantee of any lifetime. It's commercial components in space.
Yes.
What sort of permissions do you need to launch a satellite like this on the orbit?
Yeah, actually, this is one of the things that was also a spin-off from Aalto 1. So Finland actually had to get its own space law. So yes, there needs to be a permit. I'm not actually an expert what actually went into the space law in the end, but now Finland actually has a registry of its space fleet containing one entry so far. But actually this register will very quickly next year increase to a larger number. So there are a number of nanosatellite projects going on right now, and they will all get to the paperwork of getting their permission to be launched, and actually you need the frequencies with which you communicate. If you need something else than radio amateur, this is why Aalto 1 is communicating with radio amateur frequencies at the UHF. That is actually nothing to worry about there. You can communicate as you want, but if you need like our S-band, then you need some bureaucracy to get the frequencies you need, and things like that. So it's not like zero bureaucracy, but it's not like a huge amount either.
You mentioned this reboot every 60 seconds. Does this reboot involve power cycling or not?
Of the attitude control system?
Yes.
Very good question. I would say yes, but I cannot say 100% sure. But this is what I would assume, because it leads to the fact that you actually have to get another contact to the spacecraft. It's like every reboot that we have from single event upsets with the onboard computer, we lose the data from Radmann from there on, because it has to be manually switched on again. So these type of things are problematic for that reason. There is no automatic control of putting the subsystems back on inside the onboard computer. Only the essentials are actually activated every time it boots.
So there's different parts from different kind of places. So there's one from Helsinki and one from Turku and different places. Who's responsible for the main operating system or the thing that all those components connect to?
Yeah. So.
And what is it? How is it made?
So I can put back the first picture. So I can explain from here. Only the payloads, AASI, Radmann, and plasma brake, come from let's say, partners. All the rest is Aalto University. And these are modular. So, AASI, plasma brake, and Radmann, they are all sort of part of the stack. So the system works so that you have a bus going through all the instruments. And this bus is simply a PC connector. And you just build it from blocks. So it's pretty simple in the sense that the whole system can actually work without these payloads. And they can develop the spacecraft electronics completely independently of us. They simply replace the part of the stack by dummies. And everything works fine. And then you just plug in the final payload components and the computer takes over from there.
So there's a Linux computer.
Yeah.
That's running it. Okay.
Thanks for the talk. I was wondering if there's any, or if you know if there's any plans or ideas to actually clean up this debris field in the orbit, or is it even possible? Or maybe not necessary because there's still enough space.
Well, in principle, with big chunks, you can, in principle, do the cleaning. But for small stuff, you would have to imagine some sort of a net or whatever to gather it out from there. At present, the situation, although it looks dramatic, it's not that bad. So you can get out. The collisions are still rare. The thing that is worrying is the exponential growth of the launch, plus the quality of components that you use nowadays in orbit compared to the old days. So if my sort of history from space hardware comes from era when these components never failed, but they were hugely power consuming. They were very, very expensive things that you would build. So you would build your instrument from 10 or 20-year-old components, which would be sort of tested for that they will not fail. The new space idea is the opposite. You are using the best possible low power consumption electronics, but you have no guarantee that it actually survives in space. So this is the worry. If we get a lot of stuff which is not going to survive, it's going to be replaced. If it's used for commercial purposes like taking photographs, they lose a spacecraft, they will certainly launch at least one more. So there is a scenario that by the 30s we would actually have a difficult situation in orbit. But if we take measures now and try to keep the orbits clean, I wouldn't see that this would be a huge problem. But it needs to be recognized, and we need to develop means to actually prevent cluttering the orbits more.
Okay, I have a question related. You gave an example of some, let's say, applications of, I think it was referred to Radmann in particular, related to the local meteorological conditions. But could you give some more examples of what would it be useful for? The different components also, not necessarily Radmann itself. For which purposes what can we learn about Earth?
Yeah, we can learn a lot about Earth using nanosatellites. So the three things here which we have ASI, of course, the spectral emitter, is something that provides a lot of information of the Earth. So we can use it for all kinds of commercial purposes, for investigating the crops, for example, and things like that. I'm not an expert of Earth observation, but this was developed by people who are really utilizing this for commercial purposes. And the spin-off, one of the spin-offs, which is this reactor space lab, is actually attacking this problem. So they will establish a fleet of these spectral cameras and sell these images to whoever needs to use them. And of course, there needs to be a layer on top, not just providing images, but also extracting the information and giving it to the customer. But nevertheless, it is really useful in practical terms. We can also learn about, of course, about physics of the Earth environment, which is clear. All kinds of instruments, not just radiation monitors, but plasma instruments, magnetic field sensors, things like that can be flown on board nanosatellites. What is also very important is that if you think about the system, you have a vast amount of space. If you only have one big spacecraft orbiting the Earth, you get information about the local conditions in magnetosphere, for example, in one place. That would be like predicting weather in Turku by having a station in London or something like that. So you can't really get a complete picture. This new space era, where the spacecraft are cheap to launch, is providing you the opportunity to actually send a fleet of spacecraft instead of one big spacecraft. And this allows you to make measurements in very many places at the same time and gather the information and obtain a holistic view of what is happening in the Earth system. This is one important thing. What you can't do with these nanosatellites is also important. I mean, we still need big ones. For example, astronomy. We need big telescopes, big space telescopes. You can't really get, if you have an aperture of that, you can't really get the observations that you get with several meters of aperture for your telescope. So astrophysics in particular is a branch where you actually need still big platforms. But things that you are doing in situ, or things that are related to taking photographs of Earth, where you don't actually need the resolution, or the light gathering power actually, which is the thing that the aperture controls, is something that you can really foresee doing from nanosatellite platforms. So there are some things in science which can really, really benefit from this, because you can do it cheap, you can do many of them, but then there are others where this is not useful.
So let's see if there are more questions. More than a question, I have a curiosity. Can you show us again the plot of these graphics of this launching, showing this exponential, this very fast peak in 2017? There was this green line, green curve.
Yeah, it doesn't really extend to 2017, okay, but 2014, but nevertheless,
okay, yes,
here.
Yes, exactly. So somehow, I mean,
Let's go one back so you can see the whole graph. No.
So it really looks that like while the commercial are going up, all the, I don't know, military, they are going down compared to before. Do you have any idea why this is happening?
This one here.
Yeah,
it's Cold War. Cold War ended.
Okay, just
we don't
because
need
of the Cold War.
Spy
I mean, there is
anymore.
no other reason because other than that.
This is simply Cold War.
Yes.
This is Cold War. After that, no motivation to invest so much money for
espionage. And how about the other
espionage.
governments? What is the yellow line, the other governments?
The other governments means like France, Germany, European Space Agency, things like which are governmental rather than or public things rather than commercial.
Okay.
So you can see that the private companies are the ones that explode.
Yes. Is there any regulation related to that for the commercial, at least?
It depends on the nation again. So, I mean, some nations have strict regulations on what can be launched. Some nations have signed different type of contracts, for example, protecting the most important orbits, like cluttering the low Earth orbit is one thing, but also very important orbit is the geostationary orbit. And there needs to be control so that you don't destroy satellites by collisions at the geostationary orbit. So there is some sort of regulation in this.
But it's
But you can have rogue
country-dependent.
nations. So, I mean, North Korea certainly doesn't care. So.
More questions? Yes.
Still about that, is there some international bureaucracy center? Because, for example, the radio lengths and stuff like that, you can't have overlap in those.
Yeah,
if you want to do good operations.
Yeah, there is. So, for example, there is this one office in UN which is United Nations, which is regulating the use of space, actually peaceful use of space. So, and that is one thing which Finland never signed before, but with Aalto 1 actually now Finland is also signing that treaty. So there are many of these international treaties that are somehow controlling the activities in space, but in order for them to be applicable to a certain nation, that nation has to ratify the contracts. And Finland, for example, never ratified this UN contract before we had our own spacecraft. So this is something that occurs when people, when the nations become spacefaring, they will enter these type of regulatory contracts, if they wish. But if they don't, there's very little the rest of us can do.
Do you know which frequencies the S radio uses?
Oh, gigahertz frequencies, I don't remember the numbers. Yeah.
But no, they're not like secret or private.
No.
Everybody could
Yeah,
get
and you
this
can,
information.
the UHF is nice. It's radio amateur, so you can listen to Aalto 1 if you want. You
Maybe
don't need
later tonight.
You don't actually need
don't have
special
anything better
equipment.
to do.
I mean, the antenna is very, very simple. So it's very, very simple. Any radio amateur can listen to Aalto 1. Yes, not control it.
In principle, they cannot be hijacked, let's say, for control, or
Yes,
could they?
in principle, probably. In principle, yes. Why not? But who would do it?
No, competitors from other universities. Instead of launching
I
their
would not
own-
say that the competition is that fierce yet. Yeah.
More questions? Okay, so if there are no more questions, as usual, we will have here for some more time, maybe half an hour more, Rami with us. So if you want to ask him something personally and discuss about some of these very interesting research results and future perspectives, he will be here and he will be happy to discuss with you. Before thanking Rami again, I would like to say that we soon, but not soon, but in January or end of December, we will have, we hope to have the new program of the Science Cafe ready, available for you. And it will be in the Facebook page, and otherwise we will advertise it as usual. Thank you again. It was very interesting.
Thanks, my pleasure.
Thanks.